Greetings to Mr. Rifki. We are Excellent Team 11 and today we'll be presenting our ACC system.
Here is our team member. On this slide, we have Elvin Xu Jinping and Ng Zhengming. On the next slide is Lian Jiaxian, myself, and Xu Yidan.
We will talk about the introduction, objectives, block diagram, and conclusion, and we will also provide a brief but comprehensive explanation of the components we use in our system, the daily challenges and problems faced by drivers, and how our ACC system can assist them to solve these problems and the future improvements that can be done.
Hi everyone, the first part of our presentation is an introduction to adaptive cruise control. With the rapid development of society, increasing traffic demands intelligent systems to improve driving safety, efficiency, and overall travel comfort. However, human drivers may react slowly, causing unsafe falling distances, unnecessary braking, and increased accident risks. To address these challenges, we use ACC to automatically adjust vehicle speed to maintain a safe following distance using radar sensing. Therefore, our first objective is to design an ACC system based on automatic control and closed-loop feedback principles. And then, we will construct the control block diagram, evaluate system challenges, and propose practical performance improvements.
So the importance of ACC system is that it significantly reduces driver fatigue and prevents collision with another car and improves overall highway traffic efficiency.
We have 6 components in the ACC system. The first one is the radar system. It is the primary sensing device in an ACC system to measure the reflected signal from surrounding vehicles, to calculate the distance, relative speed, and position of the vehicle ahead. This information becomes the feedback signal for the controller. The second component is the driver input. It sets the desired cruising speed and preferred following distance using steering wheel button or dashboard control. This setting becomes the reference input for the control system. The next component is the electronic control unit (ECU). It can be considered to the brain of the ACC system. It processes sensor data to calculate safe following gap and coordinate throttle or brake command accordingly. So which is decide the vehicle should accelerate, maintain speed, or brake. Moving on to the actuator. The actuator executes the command generated by the controller, and it has two main actuators, which is the throttle actuator that increase vehicle speed and brake actuator that decrease the vehicle speed. And this actuator ensure the vehicle follow the controller decision accurately. The next component is the vehicle dynamic. It manages the physical force of motion, ensuring ACC speed change adapt safely to mass, road grip, and gravity. The last component is the display. The ACC display provides real-time driver awareness by showing system structure, target tracking, and critical takeover warning. This allows the driver to monitor the system easily.
When the driver turns on the ACC system and sets the desired distance, the value will be taken by the comparator to compare the actual distance of our car with the desired distance to calculate the real-time distance error signal. The error signal is then sent to the ECU to let the algorithm to decide how the car should react. The ECU will send out to the car's actuator, which is either the brake or the throttle. These two systems can act independently depending on the current distance of our car with the car in front of us. The actuator input is then fed into the vehicle dynamics, which represents the physical movement of the car, and it gives us our final output line, which is the actual distance. The feedback loop located at the bottom of the block diagram is where the sensor is located, which continuously measures the actual distance ahead and loops that data back to the negative side of the comparator, which is the summing junction, so that the system can constantly self-correct. The display block branching off the ECU is just the dashboard screen displaying the visual information to the driver, and doesn't interfere with the car's movement.
To demonstrate the working principle of this standard control system, let's look at the scenario A to see exactly how this control system works in real life. We begin with a driver setting of 90 km per hour and an ACC target gap of 50 meter. A physical disturbance occurs when a slow car suddenly cuts into the lane, and it will directly affecting our plan of vehicle dynamics. So the actual following distance immediately drops to 30 meter. The radar sensor measures this output and feed the 30 meter signal back into the closed loop. At the summing junction, the 50 meter reference signal is compared against the feedback, resulting in a negative 20 meter error, and the ECU will process this error signal. The controller simultaneously output a digital warning to the driver display and send a deceleration command to the actuator system, specifically engaging the brake and cutting the electronic throttle. This manipulated brake force slows the vehicle dynamic and effectively reject the disturbance until the 50 meter target distance is restored and the error is zeroed out.
We have identified 4 problems of ACC system. The first problem is a poor weather condition. For example, heavy rain, fog, or snow may weaken the radar signal. As a result, the radar may not detect vehicles accurately, and this will reduce the system performance and may affect safety. The second problem is the stationary object. Some ACC systems may ignore stationary objects to avoid unnecessary braking. However, this could be dangerous if a stopped worker suddenly appears in the lane. For the third problem, it is the sharp curve. On the curved roof, the radar may mistakenly detect workers in the adjacent lane and cause unnecessary braking or acceleration. And the last problem is the sensor of traction. For example, mud, dirt, and even an insect may block the radar sensor. And when the sensor is blocked, the measurement accuracy will decrease significantly.
For the first improvement, instead of relying only on radar, the system combines data from multiple sensors, for example, cameras and LiDAR, which is light detection and ranging sensors. Radar perform well in poor weather, while cameras recognize land markings, traffic signs, pedestrians, and traffic lights. Lastly, LiDAR provide highly accurate 3D distance measurements. By combining all three sensors, the system becomes much more accurate and reliable.
Having established the physical benefit of those additional sensors, let's look at how this upgrade is modeled in our control loop, which is highlighted here in the red box. In this improvement architecture, the actual vehicle speed and forward distance are simultaneously measured by the radar, camera, and LiDAR brought in parallel, rather than sending three separate signals because we're conflicting signal to the controller. These distinct data streams are fed directly into the central sensor fusion block. Within this block, the sensor mathematically integrates the data, filter out false reading, and create one single highly accurate measurement. Finally, this unified feedback signal is routed back to the summing junction. By combining the strength of all three sensors, the resulting error signal is significantly more reliable, allowing the ECU to issue much safer actuator commands.
So, for the second improvement, instead of only detecting vehicles with sensors, the vehicle can communicate directly with nearby vehicles using wireless communication. The vehicles can share informations like their current speed, accelerations, and the traffic conditions, and if there are any emergency braking. This allowed the ACC system to react even before the radar detects changes. And so, the response time becomes much faster and safety also improves.
Now let's look at how that V2V communication is integrated into our control loop as highlighted here in the red box. As you can see, the V2V network acts as one external input. Instead of waiting for our physical sensor to detect a change and send a feedback signal through that summing junction, this network feeds real-time predictive data directly into the electronic control unit. Because the ECU receives this shared information, like a car braking servo, vehicle ahead it can process the situation and command the actuator immediately. This allows our control system to be proactive, adjusting the vehicle speed even before our own radar encounter the disturbance.
In conclusion, adaptive cruise control is an advanced closed-loop control system that improves both driving comfort and route safety. The system uses radar sensor, a controller, actuators, and feedback to automatically maintain a safe following distance. Although ACC faces challenges such as poor weather, sensor blockage, and limited object detection, these problems can be reduced through sensor fusion and vehicle to vehicle communication. As autonomous driving technology continues to develop, adaptive cruise control ACC will become even safer and smarter and more reliable. And this is all from our group. Thank you.